I'll be presenting the results for the turbogen experiment. So what did we learn? So we learned that the load lever is very sensitive. If you look at the image on the right, number 4 is the T handle, and when you increase the RPMs, it's rather linear. And number 5 is the load lever, and when you increase the RPMs of this one, it's rather exponential. You might not be thinking this is hard to control, but when you're working from anywhere between 25 to 45 second delay, it can become very hard to predict what the system will do. And I know Richard's probably going to ask you where did the energy go that you generated, and it's dissipated through a resistor, and it's located on the backside of the system. Next slide. So what went wrong? So we have no fuel data for this experiment. If you look at our results, it's approximately 0, which is theoretically impossible. You need some form of fuel flow in order to run the engine. And Baron sent me what's on the right, what's expected. It has some fluctuations due to increasing and decreasing RPMs, and inherently not every cycle is identical. So why did this occur? It's most likely a sensor issue, and it should either be checked before operation or contact the manufacturer to fix it. So what does this mean? It means I can't do any of the fuel-based calculations. Next slide. So we're gonna have a ton of plotted data. This red line basically right here represents our steady state analysis. And for the compressor, we basically see that the pressure and temperature increases. Next slide. Turbine 1, we see that the pressure drops and the temperature stays relatively the same. Next slide. Turbine 2 is basically the same thing, but the temperature drops a little more. Next slide. So now we see more vertical lines, and this basically represents excitation. It's all the dotted lines, greens for maximum, reds for mid-range, and purples for minimum. And for the RPMs of each of the engines, we basically see that the engine RPM, or the turbines, the engine RPM is much greater than that of the generator. Next slide. So this is our electrical data. They're basically identical, but the current has far greater amplitude than that of the voltage. Next slide. So power generated. So the goal of the experiment was to roughly generate 1,000 watts, and as you can see from ours, we generated roughly 1,100 watts. Next slide. So at our analysis point, this is basically all the data you can collect at this specific time, which was the steady state analysis. And we also have atmospheric pressure, which we used a relative humidity gauge in lab, and I also checked it with weather tables for Baton Rouge. Next slide. So now that we have our temperatures, we can calculate a specific enthalpy by just interpolating. I used air tables and with the assumptions of steady state, steady flow, and basically that the exhaust behaves somewhat like an ideal air. If you look at the image on the right, it basically represents what each value of enthalpy is for each component. Next slide. So now that we have that, we can calculate a bunch of data, but most important is the efficiency of the power turbine cycle and the overall efficiency. If we look at the power turbine cycle, we basically have 0.37, so we have no energy coming back in order to spin the compressor. But if you thermodynamically link a free turbine to the system, you'll basically get much more energy back to spin that compressor. And this is just basically specific works and energy added to the fuel for each one of the major components that was calculated. Next slide. So, engine performance. This is basically what I can't do without the fuel flow data, but I can at least explain what you're supposed to do. So, Baron sent me the image on the right, which is an air-fuel ratio for various fuels. We use kerosene in the lab. And in order to calculate your mass flow rate of air, you first have to say that the fuel flow is equal to the mass divided by the airflow ratio, and then you would solve for mass. And then you would plug that into the mass flow rate of the fuel, which is equal to mass divided by time. And then assuming stoichiometric conditions, which is a 1-to-1 ratio, we can say that it equals the mass flow rate of the air. Then we can solve for the volumetric flow rate of the air by saying that mass flow rate is equal to the volumetric flow rate times density. And of course, you would just rearrange. And then you can solve for velocity by saying that volumetric flow rate is equal to velocity times velocity times area. This is the inlet area of the compressor. And then you can solve for your Mach number by saying that Mach is equal to velocity divided by the speed of sound, or saying that velocity is divided by the square root of kRt, where T1 is basically your inlet temperature for the compressor, and K and R are just constants. And for Mach, we're basically supposed to get subsonic, and it has to be less than 0.6. You want it to be under 0.6 to prevent choking of the engine. Next slide. So the dotted lines that I told you about that were for excitation. This is the slide where this comes up. This is for the electrical generation performance. This first table is basically at each one of these times for each line. I recorded this from the graphs. And then with that data, we can then calculate the speed ratio, resistance of the fixed resistive element, and the power output. For speed ratio, I basically just did N1 over N2. And for resistance of the fixed resistive element, it's just equal to voltage divided by your current. And for power output, it's basically just square root of 3 times your current times your voltage. And for the resistance of the fixed resistive element, I thought it was interesting how they're all basically identical across the board. And we basically see that power output increases as you go from max to min. Next slide. Any questions?